All right, geometry, let's look at conditional statements, which is not a traditional math type lesson, but it is mathematical in that you're trying to determine if you can make correct conclusions and implications from certain statements. And a conditional is a logical statement written in if-then form that contains a hypothesis and a conclusion. The hypothesis is often referred to as P, and it always follows the if statement. The conclusion is referred to as Q, and it follows the then statement. And so you often will see if P, then Q. You also will see it written as P arrow Q, means P implies Q. And one conditional is if a number is even, then it is divisible by 2. So the hypothesis is the number being even, and the conclusion is that it will therefore be divisible by 2. And another one is if the measure of angle A equals 15 degrees, there should be a degree symbol there, then measure angle A, then angle A is acute. And that is also a conditional statement. If something happens, then there is a conclusion that follows. The negation of a conditional statement is simply inserts the word not. It changes the condition. So you symbolize that with a little tilde before the P or the Q. So if the sky is blue, the negation of that would be the sky is not blue. If I say I am not a girl, the negation of that would be that I am a girl. So the negation is either the addition of not, or if not is already there, you remove the not for the negation of a statement. And then in your conditionals, we have several different rearrangements of the conditionals. And this is just going to take a lot of studying and memorization. But you have the inverse, and the inverse negates both the if and then, the P and the Q. So if not P, then not Q. So the inverse of the original one, if the measure of angle A is not 15, then angle A is not acute. And that doesn't necessarily have to be true, but that would be the inverse. The converse, you swap the order of P and Q. So instead of if P then Q, it's if Q then P. So we'll flip around that original statement we had a long time ago. If the measure of angle A is acute, then the measure of angle A equals 15. Again, that doesn't have to be an always true statement. There are other angles that are not acute, that are acute, but that would be the converse of the example we had earlier. If the measure of angle A is, if angle A is acute, then measure of angle A is 15. The contrapositive is like a combination of the inverse and the converse. You flip the P and the Q, and you negate both of them. And so the statement we had earlier was if an angle equals 15, then it is acute. The contrapositive is if the measure of angle A is not acute, then the measure of angle A does not equal 15. That would be your contrapositive. You flip the order and you insert nots into it. A biconditional is a conditional, and it can be written in if and only then, if and only if form, and it combines the conditional and the converse. And for a conditional to have a biconditional, both the conditional and the converse must be true. And so you can write P if and only Q, and you would write it with a double arrow if you want to go shorthand style. And an example of a biconditional is that a number is even if and only if it is divisible by 2. And that would work both ways. So you could say, if a number is even, it is divisible by 2. If a number is divisible by 2, it is even. Both of those are true statements. So then you could rewrite this as a biconditional. A number is even if and only if it is divisible by 2. And if you want to shorten your writing there, if and only if can be abbreviated as IFF. So that's just a little shorthand notation for if and only if you're interested in that. And then equivalent statements, when two statements are both true or both false. And so a conditional and a contrapositive are either both true or false. And the converse and inverse are either both true or false. So equivalent statements. That's a lot of definitions, and it really starts to make more sense, hopefully, as we look into specific examples rather than more generic examples. And there are some generic definitions. There are some examples right here, but let's go on and fill in a few blanks here. So a definition, if something is a definition, then it can be written as a conditional statement, if-then form, or as its converse. So both the conditional and its converse would be true for definitions. And this kind of goes back to the biconditional. A biconditional would be a definition. So going back to that example we had earlier with even numbers and being divisible by 2, that kind of is the definition of even. If something is even, it's divisible by 2. That's the definition. So we could write that as a biconditional. A number is even if and only if it is divisible by 2. And so let's look at this. So here we're talking about these examples of conditionals with perpendicular lines. So our conditional P then Q, if 2 lines intersect to form a right angle, then they are perpendicular lines. And so that is a true statement. If 2 lines are perpendicular, then they intersect at a right angle. That is also true. Now, since the conditional and the converse both produce true statements, then that could be written as a biconditional. 2 lines intersect to form a right angle if and only if they are perpendicular. That is a true statement. And the symbol for perpendicular, we'll use this a lot, is the upside down T. So if you see an upside down T, that means that 2 lines are perpendicular to each other. And you see that right here with the statement that L is perpendicular to M. Line L is perpendicular to line M. So there's a biconditional. And let's look on here. So a truth table, and a truth table is probably going to be the most confusing thing that we're looking at here. But I think, you know what? I'll go ahead and do this now. So a truth table of a statement is either true or false. And to determine the conditions under which a conditional statement is true, we do use that truth table. So kind of fill in the blank with the same thing there. So one thing to remember about a truth table is that the conditional statement P, then if P leads to Q, P implies Q, that is a false statement if it turns out that the true hypothesis produces a false conclusion. So the only way P leads to Q can be false, the only way it can be disproven, think of it that way, you're trying to disprove the conditional if P, then Q, is if P happens, but Q does not happen, then the original statement would be false. And so if you have 2 statements that have the same truth table, then they are considered logically equivalent. And so the best way I can explain this, the truth table, is to consider the statement, if it is sunny, then I will wear my sunglasses. So right now, my P is it is sunny, and my Q is I will wear my sunglasses. That's my original statement. I'm claiming that every time it's sunny, I will wear my sunglasses. So let's say you see me outside, it is sunny, and so P happens, and I'm wearing my glasses. Q happened. Well, that verifies that supports my statement that if it is sunny, then I will wear my sunglasses. But what happens if you look outside and it is sunny, but you see Carboni and he is not wearing his sunglasses? So if it's sunny and I'm not wearing my sunglasses, well, now that has shown that my original statement was a lie. I did not tell the truth when I said I will wear my sunglasses when it is sunny outside. So that would be a false statement. That has led to a disproving of the original P then Q. And so that is the one that leads to a false. The other conditions, what if it's not sunny? What if you look outside and it's not sunny, but I'm still wearing my sunglasses? Well, if it's not sunny and I'm wearing my sunglasses, does that disprove my statement that if it is sunny, I'll wear my sunglasses? And no, it doesn't. Maybe I just like my sunglasses. Maybe I would wear them all the time. So if it's sunny, I'll wear my sunglasses. But maybe even if it's not sunny, I'll wear it. That does not disprove the original if P then Q. And similarly, what if you look outside and it's not sunny and you look at me and I am not wearing my sunglasses? Does that disprove the statement, if it is sunny, then I wear my sunglasses? No, it does not. So the original statement would still hold true. So the only combination that would disprove the statement is if P happens and Q does not. And that is what would lead to the false statement here in my truth table. So hopefully that makes some sense. It was a little bit confusing to me at first, and I had to do some research and thinking about it, but there we go. So let's look at a few other examples of picking apart conditional statements. And so here, all we're doing is identifying the hypothesis and the conclusion. Remember, the hypothesis we refer to as P, the conclusion is Q. And so if an angle measures 30 degrees, the angle measuring 30 degrees would be the P, the Q, then the angle is obtuse. There is your Q. And that's really all we're doing here, just identifying the P and the Q. Basically, you're eliminating the if and the then parts, and whatever follows is the P and the Q. So if a stranger walks by the house, there's my condition. If that happens, then the conclusion is the dog will bark. So there is the conclusion. So if P, then Q. Let's go on. All right, write each sentence as a conditional and identify the hypothesis and the conclusion. So these are statements, and we're going to turn them into conditionals. And remember, in conditionals must be in the form if P, then Q. That's really crap writing, but I think that's there. If P, then Q. The words if and then must be in the conditional. Otherwise, it's not a conditional. So you literally must write IF and then THEN. So keep that in mind. A catfish is a fish that has no scales. Okay, there is a statement. Let's turn it into a conditional. And the conditional would be, if a fish is a catfish, then it has no scales. Now it's a conditional. Two complementary angles form a right angle. Okay, well, two complementary angles would add up to 90 degrees. They would form a right angle. But if I want to make that a conditional, I need an if and then. If two angles are complementary, then they form a right angle. There is your conditional. Remember, you must have, you're looking for that if and then part, that if and then part. And I forgot to identify the hypothesis and the conclusion. So let's do that. If a fish is a catfish, there's your hypothesis. Then it has no scales. There's your conclusion. If two angles are complementary, hypothesis, then they form a right angle. Conclusion. Okay, let's write the negation. So negation, remember, that's changing whether something is or is not true, or something does or does not happen. So here, the statement, the truck is red. The negation of that is the truck is not red. And the negation of the man is not tall would be the fact that the man is indeed tall. So there you go. Those are, I don't think, too bad by comparison to some of these other things. Moving on. So here we have two statements, and we're going to write all of the different combinations, inverse, converse, and contrapositive. And so this first one, so we have the if-then form. So this one's already written in that form. And we want to write the converse and the contrapositive of that. And then we need to determine if these create true or false statements. So my statement is, if two angles have the same measure, then they are congruent. All right. The inverse is not P, then not Q. So if two angles do not have the same measure, then they are not congruent. So we just took the same statement, we just inserted nots. That's what the inverse is. Now, is that a true statement? If two angles do not have the same measure, they are not congruent? Yeah, that's true. That is indeed true. Okay, the converse is where you flip the P and the Q. So converse would be if Q, then P. So my P and Q up here, P was two angles have the same measure. Q was they are congruent. So we now need to flip that. If two angles are congruent, oops, wrong button. If two angles are congruent, then they have the same measure. And that is also a true statement. The contrapositive is a combination of the inverse and the converse. You put nots in and you flip the order, or it's also the inverse of the converse. Okay, so you negate your converse, and that would be if angles are not congruent, then they do not have the same measure. So there is your contrapositive, and if two angles are not congruent, then they do not have the same measure. That is also a true statement. So this one was true all the way down. Okay, so 8, an acute angle has a measure less than 90 degrees. Okay, that one is not in if-then form. It's not a conditional. So first thing we have to do is write our conditional if P, then Q. An acute angle has a measure less than 90 degrees. If something, then something. If an angle is acute, then it has a measure of less than 90 degrees. That is true. The inverse, you negate your conditional. So we put nots in the conditional. So if an angle is acute, so we now put if an angle is not acute, then it has a measure less than 90, then it does not have a measure of less than 90. So you just negate your statement. The converse, you flip the order of the Q and the P. So now we flip the conclusion and the hypothesis. So now if an angle has a measure less than 90 degrees, so I flipped it. I put the second part first. If an angle has a measure less than 90 degrees, then the angle is acute. That is a true statement. I forgot to do the truth statement on this one. If an angle is not acute, then it does not have a measure of less than 90. So not acute, and then it's not less than 90. That is also true. Lots of true statements here. We need a false one just to shake things up a little bit. And the contrapositive is the negation of the converse. So we put nots. So if not Q, then not P. So if an angle does not have a measure less than 90, then it is not acute. And that is also a true measure. If an angle is not less than 90, then it is not. Wait. If it's not less than 90, then it is not acute. That is true. Sorry, had to do a double take on that one. Moving on. Okay, so let's look at these. Decide whether each statement about the diagram is true and explain your answer using the definitions you have learned. So what do you know, and are these true statements? And so this is, while we're not putting it in conditional form, this is kind of how the conditional thought process works. It's looking at something and determining, is it true? Can we make these conclusions based on what's given? And the measure of angle AEB, so AEB, is that a 90-degree angle? And yes, it is. How do we know it's a 90-degree angle? Okay, because it does say explain. So how do we know? The answer is yes, or that is true. And we know that because that symbol, the little right angle symbol there, that means it's a right angle. So we know what that symbol means, and it does mean that those are perpendicular, therefore 90 degrees. Points A, C, and D are collinear. Is that a true statement? So here's A, here's C, here's D, and no, they are not collinear. If you were to draw a triangle, you're drawing a triangle there. They don't lie on the same line. So the answer is false. And your reason, it's kind of an obvious answer, I think. It's kind of silly, but point D is not on the same line as AC. And AC and CA, are they opposite rays? So AC is here, starting A, going towards C, and CA is here, starting at C, going towards A. Are those opposite? And they go in opposite directions. They do, but opposite rays, this is false because opposite rays must have a common end point. These do not have the same starting point. They don't have the same end point. So do you remember opposite rays? They do go in opposite directions, but they must start from the same point. So this would be examples of opposite rays that both start with that end point. And that is not what happens here. They kind of overlap. So nope, those are not opposite rays. All right, let's see. Moving on. The conditional statement below is true. Write the converse. If the converse is true, then combine the statements as a biconditional. Okay, so the converse is to flip the order of the Q and the P. If the sum of the measures of two angles is 90, then the angles are complementary. So the converse is, if two angles are complementary, then their sum is 90. Is that true? Yes, it is. If two angles are complementary, then they will add up to 90. So they are both true statements, right? So this is true, as is the original. That means this can be written as a biconditional, which means you have the if and only if statement in it. And so the biconditional for this one would be, oh, I didn't write it. Where'd it go? Okay, it disappeared. So two angles, the sum, this is really bad writing. Two angles is 90 degrees if and only if, and you could write IFF. Whoops. Oh, I got this backwards. The sum of two angles is 90 degrees if and only if the angles are complementary. I'm going to say they are complementary. And that is really bad writing, but I'm writing this kind of quickly because I want this video to go a little bit quicker. That is sloppy writing. And for the biconditional, you can write it in either order. So I could have also said if two angles are complementary, if and only if the sum of their measures is 90. You can also say the sum of two angles is 90 if and only if they are complementary. So the biconditional could be either order. It doesn't have to be Q then P or P then Q, just as long as you have them both in there and they're tied with an if and only if statement. Oh, wait, here's the biconditional down here. I'm so stupid. I wasn't paying attention. Okay, well, here we go. If the sum of the measures of two angles is 90 degrees, if and only if the two angles are complementary. And this is what I was saying earlier. Wow. Okay, so I'll just erase all this. I spent all that time doing that. And you could write it in either order. So you can write the sum of the measures is 90 if and only if that, or two angles are complementary if and only if the sum of the measures is 90 degrees. So I kind of forgot what I was doing there with my planning. All right, moving on. Getting towards the end here. So if x is greater than 7, then absolute x is greater than 7, and that is a true statement. If you have any number greater than 7, then the absolute value of that number would also be greater than 7. So that's true, which they said in the directions that would be true. The converse is you flip the order. If absolute x is greater than 7, come on, go away. There we go. If absolute x is greater than 7, then x is greater than 7. Is that a true statement? If the absolute value of a number is greater than 7, then x is greater than 7. And no, that is not true. That is a false statement. And for false statements, it's good to think of a counterexample. And you could say, well, what if x is negative 8? Well, in that case, the absolute value of negative 8 is 8, but the original number was not greater than 7. Negative 8 is not greater than 7. So that would be your counterexample. And because the converse was false, you cannot write a biconditional. So you won't have anything here. You cannot write a biconditional because in order for a biconditional to be written, you have to have both a true converse and the original conditional. Write the two statements that form each biconditional. So here's a biconditional, and we're going to write the two conditional statements that led to the biconditional. Two numbers are additive inverses if and only if their sum is 0. Okay, so the way you would write that is two conditionals is first the P then Q. If two numbers are additive inverses, then their sum is 0. And then you flip that. If two numbers have a sum of 0, then they are additive inverses. And remember that for all conditionals, you must literally have the if and then written in your sentence. If you don't have if and then, it's not a conditional. So do remember, you must have those written. Two numbers are reciprocals if and only if their product is 1. Okay, so I need to write that in conditional form. If two numbers are reciprocals, then their product is 1. That would be the conditional. If two numbers are reciprocal, then the product is 1. Then you flip the order. The converse of that is if two numbers have a product of 1, then the numbers are reciprocals. Cool. All right, then we're almost done here. Almost done here. How many more pages? I think this is, yeah. All right. So if, rewrite the sentence statements as a single biconditional statement. If you can run for president, then you are at least 35 years old. And if you are at least 35 years old, then you can run for president. Those are true in the United States of America. So that can be written as a biconditional. And what the heck just happened? There we go. And the biconditional is that you can run for president if and only if you are at least 35 years old. So there's your biconditional for that statement. And that is a true statement. Okay. And now a truth table again, talking about the more complicated truth table. And the original true false things are the same as what we had earlier. And what we're going to do is we're going to say what happens if we negate the P. We're ultimately looking for the negation of not P then Q. And so if I change P, so now P, it was true. And if I change P to false, now not P, what I have right here, not P leads to Q, that's false leads to true. And false leads to true is going to lead to a true statement. Okay, and I'm going back to this. This is kind of confusing. I'm going to go back to the original truth table right here. And the only way P leads to Q, the only way that we have a false is if we have a true followed by a false. So if you have a true followed by a false, that's what leads to an overall conclusion of false. And so let's go back here. So right here, not P was false, and it goes to Q, which is true. Okay, so false to true, we're looking for true to false. That's the only one that leads to the false. So that was false, then true. Here, if P is true, the negation of that would be false. And now I'm curious, what if I go to the next column, not P, then Q? Well, now not P is false, leads to false, and false to false. that does not disprove the original statement. So we hold true. The original statement holds true. Down here, if P is false and we negate that false. So it was false over here. I'm now changing it to true. Now, this column, not P, then Q. So I'm going not P is T to T. Okay, that is also true. That is also true. So the one combination that disproves the statement is if you want a false leads to, you need a true leads to false. A true leads false. So here, that's going to happen on this last one. P is false originally. So the negation of P would be true. And so now I have the negation of P, which is T. So T, something is true, but it led to the false conclusion. That's the condition that disproves the original. So now the original statement has been disproven and the original statement is false. The original statement is false. Then we're doing the negation of that one, that whole column here. So if I do the negation of that quantity, then all we're going to do is flip all of these. So that's going to be false. We just change those. So we negate those, change it false. That was true. Now it's false. That was false. Now it's true. And there is a flushed out truth table for this statement right here. And it's a little bit complicated. We may do a few more examples because I know that's probably the most difficult thing conceptually to wrap your head around. But there we go. And we will talk about this more on Tuesday.